right, let's continue with the next section, subsection I should say. We are still talking about Schwarzschild spacetime. And today I want to discuss a little bit, again, as I hope, the time-like geodesics in Schwarzschild spacetime. So I guess everybody in the audience has heard about this before. So I will repeat a couple of things which you probably know. And I hope I will also address a few issues which you do not know yet. So time-like geodesics. This should be 3.3. I think I messed up the numbering here on the board a little bit, but in the written version I think it's correct. Time-like geodesics in Schwarzschild spacetime. And I will concentrate on things which are relevant if you are close to the horizon. So I will discuss again what happens to an observer who is freely falling towards the center of a black hole, of a Schwarzschild black hole. I will discuss the circular orbits, but with an emphasis on those which are close to the horizon. And I will discuss a phenomenon which you maybe do not know yet, that these are the so-called zoom whirl orbits, which take place very close to the horizon. So that's the program for today. So if we talk about time-like geodesics, in physical terms, this means we are talking about freely falling particles. So we have particles, test particles. The mass of the particle must be small in comparison to the mass of the black hole, so that the space-time geometry is not perturbed. And we throw the particles with a certain initial velocity into the space-time, and then we see how they observe, how they move around. And the equations which we need are, of course, we need a Hamiltonian, or we could use a Hamiltonian, but we usually use a Lagrange formalism here. So let me recall what the Lagrangian was for the geodesics. That's Lagrangian, where the dot means derivative with respect to proper time. For time-like geodesics, we always use the proper time parametrization. And then we have the Euler-Lagrange equations, which are d by d tau dl dx mu dot minus dl dx mu 0. So these are in general 4 equations. For this situation, fortunately, we won't need all 4 of them. And then, because this is proper time, we have another equation. We have the equation g mu nu x mu nu dot x nu dot is minus c squared. These are the equations we have to discuss. These are the equations. And we want to do this for orbits, for particles. Let me say, put it this way. For particles in the equatorial plane, and that's all we want to consider in Schwarzschild. This Lagrangian simplifies to 1/2. Well, we have a GTT, so this is minus 1 minus RS over R C squared T dot squared. Then we have a GRR. This gives an R dot squared term. And then we only have the phi dot term, R squared, phi dot squared, and that's it. There's no theta dot term, because in the equatorial plane, theta dot is 0. And theta is 0, so the sine square is 1. Yeah?
Shouldn't the derivative not be on tau, not on...
Yes, thank you. That was a writing mistake. Our parameter is called tau. You should not confuse this with the time coordinate t. Yeah, these are 2 different things. Thank you. Okay, so then if we evaluate these equations, so I write down the t equation. So this means x mu is ct. Then we have d by d tau of what? Of minus 1 minus RSR T dot. So if I take the derivatives, the 2 cancels the 1/2. So this is this term. And then I get a 0, because my Lagrangian doesn't depend on t. Yeah? The coefficients are independent of t. So that's it, and this means we have a constant of motion. So this thing is a constant of motion, and it's usually called the energy. Well, actually, in my GR course, I use the symbol E for this quantity. I think it's better to use it for this quantity. If this is a constant of motion, then this, of course, is also a constant of motion. Yeah? And well, this really is energy per mass. Yes, that has the right dimension. So the Lagrangian, there's no mass. The mass of the particle is not written here. Yeah, so it drops out of from all equations. That's the reason why we don't write it. So when we say energy, then actually we mean energy per mass of the particle, not mass of the black hole. So this should have the dimension of energy divided by mass. T dot is dimensionless. Yeah, time divided by time gives something dimensionless. It is also dimensionless, and then we would need a c squared in order to get something with a dimension of an energy. So one should use it in this way. So if you compare with the notes of my GR course, those of you who have this, then the E is defined in a slightly different way. So you have to amend these factors everywhere when you compare. And then we write down the phi equation. This is also very simple. Tau, if I take the derivative with respect to phi dot, there's no phi dot here, it's only here. The 2 again cancels the 1/2. That, by the way, that's the reason why one writes the 1/2 here, yeah, because it usually cancels against a 2 which comes from the derivative. And we have just r dot phi dot, and again there's no phi dependence, so we have -0, and the whole thing is 0. So we have another constant of motion, and that's what is called angular momentum, or rather angular momentum per mass. That's r squared phi dot. And then there is, of course, also the r equation, but I don't write this, because I have as a third equation, I have this. And the 3 equation, the 2 which I already have, and this one, will determine everything already uniquely. So I won't need the r component of the Euler-Lagrange equation. Of course, it holds, and you can check that if the 3 equations which I write down now are true, then the Euler-Lagrange equation for r is automatically true. So the third equation is this here. Now for our metric coefficients, c squared t dot squared plus r dot squared 1 minus rs over r dot phi dot squared is minus c squared. So now we have 3 equations. Let me call them A, B, and C. A, B, and C. And that's the equations we have to solve. They determine the time-like geodesics. Where the first equation gives you the t dot in terms of one constant of motion. So let me solve for the time derivatives, yeah, proper time derivatives of the coordinates. So t dot is E divided by c squared 1 minus rs over r. So this is now an equation of A prime. This can be solved for phi dot, and it gives me the phi dot. This is L over r squared. This gives me a B prime. And now let me see if I am able to solve this for r dot, or rather for r dot squared. So I begin with this term, r dot squared. Then I have to multiply everything with the 1 minus rs over r. Then comes a curly bracket. So this goes to the other side. It is 1 minus rsr c squared, and now t dot squared. And t dot squared is e squared divided by c squared 1 minus rs over r squared. It's a c to the 4, right? I have squared this thing. So that's on the right-hand side. Then I have this on the right-hand side, minus r squared phi dot squared. That's L squared over r to the 4th. And I have a minus c squared here. And I can simplify this a little bit. So this obviously goes away. This goes away. And this goes away. So I have, if I multiply this out, I have e squared over c squared. Then I have minus L squared R squared. No, this is in the numerator. Minus RSR minus c squared. Okay, and that's my equation, C prime. So these are the equations we will now evaluate. And I do this in two steps. I first discuss the radial geodesics, where the particle just move. I will discuss them briefly. Where the particles just move on a radial line. Then obviously this equation becomes trivial. If for motion on a radial line the phi dot is 0, this means L is 0. And so this equation decouples from everything else. I have just these two equations with L equal to 0. And let me work this out. So I do now, this is a radial motion. Radial motion means phi dot equals 0. And this implies L is equal to 0 from this equation. And then I have T dot is, I cannot do anything with this, c squared, so this would be a double prime, and the last equation is r dot squared, it's e squared over c squared. This is 0 because L is 0, minus c squared 1 minus SR. This is C double prime. These are the two equations. These are equations for T dot and R dot. Of course, we are still free to choose an initial condition. We can choose initial condition where we put the particle and where we give it a certain initial velocity. And I want to work this out for the case that we drop the particle from a certain distance. So we put it at a certain distance, RO say, and then we just let it go with initial velocity equal to 0. So the initial condition we want to discuss is that R dot at a certain radius R equal RO is 0. So the equations we have written down hold for R bigger than RS. This form of the metric is valid for R bigger than RS and also for R smaller than RS. Not exactly at RS. There the coordinate system breaks down. But we can consider particles moving in the safe region outside of the horizon. We can also consider particles moving inside the horizon. And now the question is this initial condition meaningful for both cases? That's a question to the audience. Is this a meaningful initial condition for values R naught which are bigger than RS or smaller than RS? Any opinion?
Beyond RS, I think not.
Yes. So for R naught smaller than RS, this is not possible. Why is it not possible? Because the R coordinate becomes time-like there. This means if I stay tangent to an R line, then that was the wrong way of putting it. Maybe let me draw the picture again. Oops. So here is RS. And now we have inside the light cones in such a way. They are like this here. These are the light cones. So you see, if you want to stay at this is not meant to be at the horizon. So if I want to have my velocity at this radius value R naught tangent to the T line, then it would mean that my initial direction is space-like. As a particle moves at a speed bigger than the speed of light, and that's not allowed. So this makes sense only for initial velocities bigger than RS. So we are outside of the horizon and we let the particle drop, and then we want to find out how it moves. So we can determine with the help of this initial condition the constant E from this equation, namely from, I use both equations actually. So I just write down this here. So T dot at RO is then E divided by c squared 1 minus rs over rho, right? If I insert rho on both sides, then I get this equation. So this is my equation, a double prime specified to this case. And here I get a 0 is e squared over c squared minus c squared 1 minus rs over. Didn't I? No, I think it's correct. I think it's correct. And this means that I have determined my constant e. Yeah? So from this equation down there, I get my constant e. What is it? Or rather e squared. E squared is c to the 4 times 1 minus rs over rho. And now you see also from the equation that it only works if rho is bigger than rs, because obviously the square should not be negative. Yeah? So it only works for rho bigger than rs. If we insert this, now we get our equations for t dot and r dot. T dot is e, so e is the root of this. Let's choose it positive. What does this mean? It's e is positive. This means that the time coordinate and the proper time run in the same direction. Yeah? So both coincide what's the future direction. Mathematically, you could also work with a parametrization of the curve which runs from the future into the past. But that's not a very common physical convention. So and here I have c squared 1 minus rs over r. So that's the equation for t dot. That's now a triple prime. And for r dot squared, I get e squared over c squared. This is c squared 1 minus rs divided by r naught minus c squared 1 minus rs over r. I think I can simplify this a little bit. These two terms drop out, right? So this is c squared rs over r minus rs over r naught. Okay, so these are the equations which we can solve now. Actually, you can integrate this for an arbitrary value of rho bigger than rs. You can write down the solution. So by the way, if you choose r naught equal to infinity, then you get precisely the Perlick-Wigglesland observers. They were dropped from infinity, right? So if you choose r naught equal to infinity, then the equations of motion should coincide what we had for the Perlick-Wigglesland observers, and I hope it does. And, but that's not the case what I want to consider here. Here I want to consider the limiting case when rho approaches the horizon. That's possible. Yeah? So this must be, rho must be bigger than rs, but the limiting case is just allowed. Then it gives me e equals 0. So in the limiting case, rho to rs, we get what? We get from this equation here a reasonable limit. We get this is c squared rs over r minus 1. So what we do is we drop the particle from the horizon. Yeah? We put it on the horizon and then we let it go with in a limiting case. Actually, you see from this picture already at the horizon the particle would have to move at the speed of light, yeah, because the horizon is light-like. But in the sense of a limiting procedure, it is allowed. Yeah? And that's what we want to discuss now. And what we want to calculate is, of course, the time until the particle arrives at the center. It must arrive at the center because the light cones are tilted. They are open to the left. So the particle can only go inside the light cone, so it must arrive at the singularity. And we want to calculate the time from this equation. So r dot means the r by d tau. So this means the r by d tau with a plus or with a minus is c root rsr minus 1. So which sign do we want to choose? Well, we want to have the particle ingoing. We drop it from the horizon, so it moves inward. This means r dot must be negative. So we have to choose the negative sign. The minus sign. And then we get the following. we get minus dr root rsr minus 1 is cd tau. And that's an elementary integral. You can look it up. So the total time, the total proper time which it takes the particle to arrive at the center is integral. It starts at Rs and goes to 0. That's the integral we want to calculate. dr root Rs over r minus 1. Of course, we can make this into a plus sign if we just exchange the limits. So we can write it in this way. dr root Rs over r minus 1. And that's an integral which you can look up in the table, or you can let Mathematica calculate it for you. And what you get is the following. This is minus root r Rs minus r plus Rs arcus tangent root r over r minus Rs. No, the other way around. Rs is bigger than r. The other way around. That's it. 0 to Rs. So let's insert this. At the upper bound, this gives you 0 if r is equal to Rs. And here, if I set r equal to Rs, I get the arcus tangent of infinity. Okay, that's the upper bound. And the lower bound, then this gives a 0, and this also gives a 0. Yeah, arcus tangent of 0 is 0. So this is minus 0. And where takes a tangent the value infinity? At pi half, if I'm not mistaken. Yeah, tangent of pi half is infinity. So this is Rs times pi half. And that's the result. So the travel time of our particle, which is dropped from the horizon and then moves through the black hole towards the center, the total travel time is Rs over c times pi half. Well, if we are just interested in the order of magnitude, then we can forget about the pi half. Then it's just Rs over c, and this is just the time which light would need in order to travel the distance Rs. Yeah, according to elementary kinematics. Yeah, so this gives you the right order of magnitude for a freely falling particle. We are not talking about light. We're talking about particles, massive particles. They, of course, do not move at the speed of light. But the order of magnitude which comes out is to a very good approximation what we get from just this naive idea that the light ray travels the distance Rs at the speed of light. And if you want to insert numbers, so let's say for Rs, well, let's do a supermassive black hole. So if M is, well, for the thing at the center of our galaxy, we know with very high accuracy that the mass is 4 million solar masses. This means that Rs is 2gm over c squared. So it scales with a mass, and now everybody should be able to say what is Rs for this value of m without looking up g and c in a table. How could you do this? Well, you see it's just proportional to the mass, so it scales with the mass. And I hope everybody knows what the Schwarzschild radius of a solar mass is. So you just have to multiply it with 4 millions. So what is the Schwarzschild radius of a solar mass? 3 kilometers about. We have to multiply it with 4 million, so we get something like 12 million kilometers. 12 million kilometers, what is this in comparison to the Earth's radius, for instance? So if we map this thing, this surrounding of the supermassive black hole onto our solar system, where would be this distance? So the radius of the Earth, at what's the radius of the orbit of the Earth? 150 million kilometers, so it's considerably more than this. Yeah? So this is well inside the orbit of the Earth. It's even inside the orbit of Mercury. Yeah, so that would be the Schwarzschild radius of the black hole at the center of our galaxy. And now we can calculate the delta tau. The delta tau, well, this is just it is just the time which it takes the light to run through the distance of 12 million kilometers. So it's something like 12 million kilometers divided by, well, the speed of light. I think everybody knows this. This is 3 times 10 to the 5 kilometers per second, right? 300,000 kilometers per second. And then there's a stupid factor pi half, which is not very relevant. And I think we can cross out here a couple of things. So this gives just 40, right? And divided by 2, it gives 20. So this is about 20 pi seconds. And pi is something like 3, so it's approximately 60 seconds. A little bit more than 60 seconds, say 63 or something like that. So that's the time it takes you if you go to the horizon of the thing at the center of our galaxy, let yourself drop from the horizon, and this is the time until which you will arrive at the singularity. If it is a Schwarzschild black hole. If it is a Schwarzschild black hole, yeah. So actually a little later we will discuss the same question for a Kerr black hole, for a rotating black hole, and there will be a few changes. In particular, the most important change is that the singularity is no longer a point. The singularity is a ring, and you have a certain chance to dive through it. So you are not necessarily torn apart if you come close to the center of a rotating black hole. You are necessarily torn apart if you come close to the center of a Schwarzschild black hole. So now you might expect that, of course, the time will be shorter if you let not yourself drop from the horizon, but if you rush through the horizon. That's what this character Cooper did in the movie Interstellar, right? So if I interpret the picture correctly, then he really rushed through the horizon with an acceleration towards the center. So you would not be surprised to find out that he would have arrived at the center quicker than according to this formula, if it is a Schwarzschild black hole, what he was entering. But the surprising thing, those of you who have taken my GR course know this, but I really want to repeat it for the other ones. The surprising thing is that you always get a smaller time, whatever you do, if you are inside the horizon. And that's even if you use a thrust in order to get away from the center, which would be the most natural thing to do. Yeah, if you are in a rocket, you have a thrust, and you fire it up, trying to get away from the center. This makes things worse. And the quick calculation which shows this is the following. So for arbitrary, this was free fall. We used the geodesic equation, yeah. But for arbitrary time-like curves, time-like curves in the domain between R and Rs, we have the following. Well, let me just write down the condition that we use proper time parametrization, which was minus 1 minus Rs over R, there's a C squared, T dot squared plus R dot squared, 1 minus Rs over R plus R dot phi dot squared is minus C squared. This holds for any kind of motion as long as you move at a subluminal speed and use proper time for the parametrization. And now you see if you are inside, then this bracket is negative. So with a minus sign in front of it, the whole thing is positive. And also this here is positive. It could be 0. Phi dot could be 0, but it's certainly bigger or equal than 0. You could also write this here. It doesn't matter for the argument. So what we find is that R dot squared, this here is negative, right? This here is negative. So let me write it in the other way around. Let me write it the other way around. That this here is, what is it now? This is bigger than minus C squared. Yes, that's it. Have to be careful with the sign, because if you multiply the whole thing with a minus, this is negative. Is that true? Let me see. R is smaller than Rs, so this is bigger than 1. No, this is bigger than 1. What did I do? I have it this way. I have it this way. I wrote the same expression as here. I just wrote it in a different way. I changed the summits. So that's what I have. Now if I want to multiply the whole inequality with a minus sign, then the sign turns around. So I get r dot squared rs over r minus 1 is smaller or equal than c squared. Oh, but that's wrong. What did I do? So r dot should be bounded by above from below.
You don't have to change the inequality sign, right? You multiply with both sides with the...
Yeah, but if I multiply with a negative number, then the inequality sign turns around, right? Okay, what did I do? I just copied this here. On the other side, I copied this here, and this is bigger than... nonsense, nonsense. So this thing contains these bigger terms, so this is a bigger one. This is a bigger one. That's it, and then now it's correct. Now it's correct. That's it. So I dropped, from this side, I dropped positive terms. So I get on this side something which is smaller than as it was before. So now it's correct. And now you see, you can integrate this, so you get something like dr over root rs over r minus 1. I don't care about the sign. So this is certainly true in this way. Yeah. And you see that if the r cannot be 0, yeah, so it's not allowed to move in the direction of tangent to a t line. So this is monotonic. So if we integrate it now, there cannot terms cancel on this side. That's the reason why it was allowed to do the absolute sign here. Yeah, it cannot change sign. And the maximal domain which is available is the domain from 0 to rs. So I certainly get that the integral from 0 to rs over this expression here must satisfy this inequality. And this holds for any motion. The particle may do whatever it will. So we have this equality. And you see, this was exactly the integral we have just calculated. Yeah? So we see that for an arbitrary motion, we get a time which is shorter. Whatever the particle does, it will end up in the singularity quicker than if you do it in free fall. So that's a very important thing to know if you ever happen to fall into a Schwarzschild black hole. And that's what I wanted to repeat about the radial motion, because I think this is really something which you should know if you deal with black holes. And now I talk about non-radial motions. And for that, I will begin with a circular motion, with a circular orbit. Oops. So, I think I remove this here. So for non-radial motion, we can use the coordinate phi for the parametrization. Of course, this doesn't work for radial motion because there phi is a constant. But for non-radial motion, we can use the parameter phi. And if you have r as a function of phi, this will just give us the shape of the orbit. For most purposes, this is all you want to know. So that's what we want to discuss now for the bound orbits. I'm not sure it was a good idea to erase this, because I need these three equations, A, B, and C, of course. Oops. So I have to reconstruct them. So I do now B, non-radial motion. So for that, I want to derive an expression for dr by d phi squared. This would give me r as a function of phi, the orbit parameterized by phi. And of course I can write this with the help of the chain rule in this way. So I need these two expressions, and that's as nonsense. R dot and phi dot. That's what I want to calculate. I had expressions for r dot squared and for phi dot on the board, which I unfortunately erased, but I have them here. So I hope it's the same in my notes, which I had on the board. So I have here for the r dot squared e squared over c squared minus 1 minus rs over r, L squared over r squared plus c squared. And for the phi dot squared, that is certainly the same. This was L squared over r to the 4. So I remember that this was true. So we can rearrange this a little bit, order by powers of r. So first of all, I write the r4 in the numerator. So I have r4, and then I have to divide this by L squared. Let me do this. E squared divided by L squared c squared. I multiply this out. Minus L squared divided by r squared divided by L squared. So this gives 1 over r squared. Minus c squared divided by L squared. Plus rs over r cubed. L squared cancels, and plus rs over r c squared over L squared. So the bracket closes. And now I can collect equal powers. So I have a fourth order term. That's the highest order. E squared over c squared L squared. And where else? Here, this is also, no, here, this is an absolute term. Minus c squared L squared r to the 4. Then I have an r to the 3 from this here. Plus rs c squared over L squared r cubed. Here I get an r squared. And I also get an r from this term, plus rs r. And you see that's a polynomial of fourth order. And this determines my orbit. And the usual thing is to introduce a name for this, to use this as a kind of potential. Well, for some convention, let me write a factor minus 2 in front of it. And then it's a potential which certainly depends on E and on L. So let me indicate this by the indices. So that's how I abbreviate this expression. And if I read this equation, then I see that I have something like 1/2 dr by d phi squared. I take this to the other side, then it becomes plus v EL of R is 0. And this looks like an energy conservation law. Yeah? That's like a kinetic energy, a velocity squared, and the m and the c squared. Let's forget about the c squared. Maybe I have made a mistake. Maybe there should be a c squared somewhere. Doesn't matter. It's just the general structure, the analogy with an energy law. Yeah, this is something like a kinetic energy, velocity squared, and this is something like a potential. And from this equation, you can read a lot of properties of the orbit if you just know this expression, and we know it, it's written here. So for instance, if we have something, let's assume that for certain values of E and L, yeah, V depends on E and L, it takes different shapes for different values of E and L. Let's assume it has something like this, it has a shape like that. Then we know that here is a bound orbit. An orbit which oscillates between these 2 points. Why is that? Well, this equation can hold only if this here is negative. So motion is possible only if our graph is, this is R, our graph is below the horizontal line. And here, this distance gives the velocity of the particle. Yeah? Because the velocity and velocity squared and the potential should add up to 0. So we see here, the particle is fast. It has a high velocity. Here's the highest velocity. Here it is slower. Here the velocity is 0. Here also the velocity is 0. And so what the particle does is it oscillates between these 2 radius values. It's only the radial motion. The phi motion is coded in the L. Yeah? If you want to know the phi motion, how it proceeds in the phi direction, then you have to use this equation that phi dot squared is L squared divided by r to the 4. So this here would be a bound orbit. So if our potential has this shape, and actually the bound orbits will be something which we will discuss in a minute. We could have something like that. If for some value, for some pair of values, the potential has this shape, then we would have a circular orbit. Yeah? So this particular radius coordinate is possible, but everything close to it is impossible, because here the velocity squared would have to be negative, which is impossible. So this would be a circular orbit, and actually it would be a stable circular orbit, because if you perturb the parameters a little bit, then you get something like that. You get a neighboring orbit which is bound. And that's what we mean when we say a circular orbit is stable. That close to it there are bound orbits, which oscillate between a maximum and a minimum. So this here is a stable circular orbit. And we will determine the stable circular orbits in the Schwarzschild metric in a minute. And if we have something like that, if our potential has a minimum on the axis, but if it is a maximum, if it is something like that, then again we have a circular orbit. Yeah? So our particle can sit here. It has speed 0. The r by d phi is 0. So it sits there. It doesn't move. But if we perturb it a little bit, if it is either here or here, then it has a velocity different from 0. So it goes away. Yeah? So neighboring states are possible in the sense that the particle goes away, and this would be an unstable circular orbit. So if we want to determine, that's the first thing we will do, the stable and the unstable circular orbit, we have to solve the equations v is 0, v prime is 0, and v double prime is positive. And for the unstable case, v is 0, v prime is 0, and v double prime is negative. And when we have done this, then we will go to the general question of orbits, and we will discuss what orbits are possible. So, but let's do the circular things first. So the circular orbits. So they have v, el of r equals 0 and v, el prime of r equals 0. And they are stable if v, el double prime, nonsense, is positive. Is that right? Yes, a minimum has a positive second derivative, right? The pitch, the increase is becoming bigger. Yeah, it's positive. And unstable if the other equality holds. If VEL double prime of r is smaller than 0. If it's equal to 0, then you have to look more closely. Yeah, then the second derivative alone doesn't tell you what's going on. Could be anything. Okay, so we will now evaluate these equations. So let's determine the circular orbits. So we have to write the equation. This is 0. And actually, yeah, so I just copy this. So I have to divide this by -2, the left-hand side. So this is, I can write it on a common denominator, c squared L squared. Then I have a 2 here, and I have a minus sign in the numerator. So I have c4 minus e squared. So and this divided by -2 gives minus rs c squared divided by 2l squared r cubed plus 1/2 r squared minus rs half times r. So this, and this is 0 for a circular orbit. This equation alone doesn't tell you that you have a circular orbit. Actually, this is true also here, right? V is 0, also here at this point and at this point, but this has nothing to do with the circular orbit. You also need the property that it is an extremum, so you also need that the derivative is 0. So let me see if I can calculate the derivative of this thing. So here I get 2 times c to the 4 minus e squared c squared l squared r cubed. Then minus 3/2 rs c squared l squared plus r minus rs half. And of course we want to determine the constants of motion E and L, so we want to eliminate them in order to find out at which radii we have circular orbits, and then in the next step at which radii we have stable circular orbits. So in order to solve these for the constants of motion, I think, anything wrong?
In the second term and the derivative.
Yes, thank you. Of course. R squared, and what did I have here? So this was R minus rs half. I think I'd realize it in a minute, because I want now to multiply the two equations with appropriate factors so that the first two terms cancel each other. Then we have the E dropped out, and then we can solve for L. Yeah? Yeah? Question?
Yes. What was the reason to divide by minus 2?
Yeah, just this.
To 0, so,
just this, yeah. Yeah, the analogy with kinetic energy.
But you said VEL to 0, so then you divide it by minus 2.
Yeah. Actually, you can multiply it with an arbitrary function which is not 0. Yeah. So actually, you will find this in the literature. Yeah. Different authors use different versions for this effective potential. And the reason is just it's just this, that you get exactly the same results if you multiply it with anything which is not 0. Yeah. Yeah, it's a pure convention that I have this formula here with a 1/2, which we are used to from the kinetic energy. Absolutely not important. So I want to have the same factor here. So I think I multiply this with a 4, and I multiply this with r, right? Then the first two terms are the same, and then I subtract the results. So I get 0. These two terms drop out. Then I have 4 times this here. This is minus 2 rs c squared l squared r cubed, and this goes away. There's minus 3/2, so I have minus 3/2 here. And then here I have plus 2 r squared minus r squared minus 2 rs r. Oops. Minus 1/2. Is that true? No, plus. Yeah, I subtract the second equation from the first. So I get minus. So I have this here. This looks better. What is here? Here the sign was correct, right? Minus. Yes, this becomes plus. This here becomes minus. Yes, I think it's correct. So let's see, we will realize in a minute. So 2 minus 3/2 is 1/2, right? It's 1/2. This is just a 1. And this is 3/2, right? So, and I see that I can divide by r squared, and this goes away. Where's my L? I should have an L somewhere. I forgot it here. I want to solve for L. It would be very bad if the L had been dropped out. So I want to solve for this expression. So I get, let me do it slowly. I'm not so good at this kind of calculations. So this is on the left-hand side now, and here I have r minus 3/2 rs. Oh, this looks good. I think I get the right result. So if I solve this for L squared, yeah, I just have to write this in the numerator, rs c squared r squared, and I have to multiply this with a 2, then I get 2r minus 3rs. And now you see already it doesn't work for all the radii. Yeah? It only works for radii which are bigger than 3½ rs. So circular orbits, free fall orbits, are possible only at radii are bigger than 3½ rs. So that's what we get from L squared. We have to check if we get anything else from E squared, but actually we won't. But we have to be sure, of course, that, so this is our first important result. This gives the L squared for the circular orbits. For any circular orbits, we have not yet talked about stability or instability. And now we have to determine E. We can do it from either of these two equations. I think this is a simpler one. So we have 0 is, I multiply with c squared L squared. Then I get 2c4 r cubed minus 2e squared r cubed. I have multiplied with c squared L squared. So I get on the other, I get minus 3½ c to the 4 rs. And r squared, rs, not the power of s. And then plus r minus rs half c squared L squared. So I can solve this for E. Well, let me do it slowly. 2e squared r cubed is 2t to the 4 r cubed minus 3½ c to the 4 is r squared. And then the thing we have just calculated, c squared L squared, I read from the bottom line. Rs c to the 4 r squared divided by 2r minus 3rs. And I think we can divide by a certain power of r. Yes, by r squared, r squared, r squared. And I think I have to multiply this out. 2e squared r is 2r minus 3rs. Here I can take a c to the 4 out, nothing else. 2r minus 3½ rs. And then the numerator, the denominator. And plus rs half rs c to the 4. Okay, let's multiply this out. 2r minus 3rs. I have a c to the 4 in front of everything. And now let's multiply this out. 4r squared minus 6r rs minus 3r rs plus 9½ rs squared plus rrs minus rs squared half. And now I'm really curious if this works out nicely. I'm afraid it does not work out nicely. Let me see. Minus 6, minus 9, minus 8. Let me see. I'm fairly sure this is not correct. 4r squared minus 9 plus 1 is minus 8. rsr. And plus 9½ minus 1½ is plus 8½ is plus 4. Ah, it does. It does. Sorry, it does. Very good. 2r minus 3rs. You see that's the square, what we have in the numerator. This is 4 times c to the 4, and now I have a square. R squared minus 2rsr plus rs squared. This is r minus rs squared. And that's fine. So I have found my E squared also. My E squared is R minus RS squared. Actually, this becomes 2 because I divide by this 2. And I have R times 2R minus 3RS, and that's correct. So we see this gives the same condition. Yeah? R must be bigger than RS. We cannot have circular orbits at radii smaller than RS. We knew this before. So the numerator doesn't give us any restrictions, and the denominator gives us exactly the same restriction as this here. So circular orbits exist. Circular orbits exist for nonsense. What is it? 3/2 RS. In this domain. How is this in the Newtonian case? If you just have the Kepler potential, at which radii can you have circular orbits? Arbitrary, yes. So here the lower bound in the Newtonian case would just be 0. You can have a circular orbit at any radius between 0 and infinity, and actually it is stable for all values. So we will check here for which values the circular orbits are stable. Actually, who knows what happens at this limit? So why is it not possible to have a time-like geodesic at this radius? Yes, you would have to move at the speed of light. We will see this in the next lecture when we talk about light-like geodesics. Yeah? So if you want to move freely, geodesically, at this radius, you would have to do it at the speed of light. Only a light ray can do this. Not an observer, what we consider here. Okay, I think I have to erase a bit. So we check now which orbits are stable and which are unstable. And then we can move to the arbitrary bound orbits, to the non-circular ones. Yeah, let me erase this. So we now have to calculate the second derivative of the potential and to see for which radius values in this allowed range it gives us a positive value and for which it gives us a negative value. Okay, so let's check stable or unstable. So what we need is, we need the second derivative. Let's calculate this. Here is the first derivative. So I have to differentiate this another time. So then I get 6 c to the 4 minus e squared divided by c squared L squared r squared minus 3 rs c squared over L squared times r plus 1. That's it. And we have calculated e squared and L squared, so I just insert these values now. So this gives, well, actually we want to know if this is negative or positive. C squared L squared is certainly positive, so we can multiply the whole expression with c squared L squared without changing the sign. So let me do this. Let me calculate this here, because this is a little bit easier. And I have 6 c to the 4 r squared minus 6 e squared r squared minus 3 rs c to the 4 r plus c squared L squared. And now I insert e squared and L squared, which we have just calculated. 6 c to the 4r minus 6 e squared r squared. 6 e squared, is this really a 12? Oh, let's see if this comes out correctly. 12 c to the 4, yeah, it could be c to the 4 r minus rs squared. And I multiply with r squared, so I have 1r in the numerator. 2r minus 3rs. I just copy this term, rs c4r, and I insert L squared from this box times c squared. It gives rs c to the 4r squared divided by 2r minus 3rs. Oops. Okay, I think I can combine these two things. Then I have 3 c to the 4 r 2 minus 2r minus rs. No, what is it? There's a power. I forgot the square here, right? There was a square. Then it looks better. Okay, now it's fine. Let me write everything on the same denominator. Then I have to multiply this with 2r minus 3rs. Then I get minus 12 c to the 4 r minus rs squared. And this one is still missing, right? Plus rs c to the 4 r squared. Oops. So this gives what? 3 c to the 4 r. I have to multiply this out. 4r squared minus 2r rs minus 6r rs plus 3 rs squared minus 12 c to the 4 r squared minus 2 rsr plus rs squared is rs c to the 4 r squared. Oops. We know already that the denominator must be positive, right? Because otherwise these equations couldn't hold. So the sign is determined by the numerator. So let me see. I have everything has a C4, right? Yes, everything has a C4. Then I get here 12 r cubed. This is minus 8. 3 times 8 is 24, right? Minus 24 r squared rs. 3 times 3 is 9. 9 r rs squared. Minus 12. Now the c is in front of everything. Plus 24 r squared rs minus 12. Oops. 12 r rs squared plus r squared rs. And if I had made everything correctly, then a lot of terms should cancel. Let's see. 12 r cubed, very good. 24 r squared rs, very good. 9. Let me continue on the other board. Oops. So what we have calculated was c squared, oops, L squared VEL double prime of r. Oops. And we end up with c to the 4. 9 rrs squared minus 12 is minus 3. Plus r squared rs. Very good, we get the correct result. 2r minus 3rs. So this is positive. That's what we want to have for stability. This is positive. Well, this is positive. Nonsense, the factor is positive. This here is positive. So this makes the decision. So we must have r times rs is also positive. So we must have r bigger than, bigger than 3rs. Yeah, that's 6m in ordinary units. Yeah, if we set g and c equal to 1, then this is just 2m, and this is just 6m, and that is what we call the innermost stable circular orbit. So this here, this value, 3 times rs, is called the innermost stable circular orbit, the radius value, and or abbreviated, usually ISCO. So let's draw this on an r-axis. So we have somewhere here 0, we have here rs, we have here 3/2 rs, and we have here 3 rs. And we know that here we have stable circular orbits. Here in this domain, we have unstable circular orbits. And here in this domain, we have no circular orbits. When I say orbit, in this context, I mean freely falling particles. Yeah? Of course, in this domain, we can have circular orbits if they are accelerated. Yeah, if you have a rocket with a thrust, then you can orbit the black hole at such radii. Yeah, that's not forbidden. It's forbidden here, because you cannot, in this domain, because you cannot stay at a fixed radius coordinate. But in this range you can. But you need a thrust for this. You can also orbit at the photon orbit, yeah? With a rocket. You need a thrust for this. You cannot do it in free fall, but you can do it with a thrust. So you have to be careful what we mean when we say circular orbit. When we say circular orbit, we mean freely falling circular orbit. So you shoot off the particle tangential to the radial line with a certain initial direction, but then you let it go. Yeah? You do not accelerate it any further. And yeah, the new and interesting feature is that here we have this ISCO. This means that if we have such a Schwarzschild black hole, and now there's matter orbiting, actually that's what we expect to happen near more or less any black hole. Yeah, there's matter coming in from somewhere, and then it goes into an orbit around the black hole, and for at least for a certain percentage of all the particles, it's not unrealistic to assume that they move in circular orbits. You see that they cannot do this at a smaller radius than the ISCO. So if you have such a thing, which is called an accretion disk, then the inner boundary of this accretion disk would be bigger than this ISCO. It cannot be smaller than the ISCO. So this will also be different for a rotating black hole. So here you have between the ISCO and the horizon, you have a certain range where no stable circular orbits are possible. That's different for a rotating black hole. Yeah, if its spin is sufficiently high, then you can have a stable circular orbit arbitrarily close to the horizon. Actually, that was also used in the movie Interstellar, because they were orbiting for a while on a planet, the black hole, and then they were aging very strongly during this period. And this could only happen for a strongly rotating black hole, because otherwise this aging effect would be fairly small, because it couldn't come sufficiently close to the horizon. But actually we may do a little exercise on this and really calculate how strongly you would age if you orbit on an ISCO in comparison to an observer who is far away. The effect is not very strong actually, but for a Kerr black hole it can be considerably stronger. Okay, so these are the circular orbits. How much time do we have? 20 minutes. I think that should be enough. And on the basis of these observations, which are quite crucial, and I think it would be good to commit this to your memory, On the basis of these observations, we will now discuss the totality of bound orbits. Here's a non-circular bound orbits. So, arbitrary bound orbits. Do I have the potential still on the board? Yes, very good. The potential is still on the board. Maybe I write it again, because I will need it in the following. I will continue this equation, so I want to have it on the board again. So I just copy this line from here, C4 minus E squared divided by C squared L squared R to the 4 minus RSC squared divided by 2L squared R cubed plus 1/2 R squared. Oops. Minus RS half R. So our goal is now to determine the totality of all bound orbits, meaning we want to find out for which minimum and maximum radius such orbits are possible. Having observed that circular orbits are not possible for all radii, so I think it's now not a very far-fetched hypothesis to assume that also the bound orbits in general are restricted in a certain way, and that's what we want to find out now. So we want to find out the allowed values for minimum and maximum radius of the bound orbits. Actually, we'll use a different parametrization, the so-called simulatus rectum and the eccentricity, because this is more convenient, but it contains the same information as what I've said. So I will continue here. I will write a couple of equations here, but let me first draw a picture. So what we need for a bound orbit, we need something like that. Yeah? So the graph of our potential, V, must have a portion where the function lies below the line V equals 0. And yeah, it has two intersections here. Then I have bound motion possible in this range. And now look at this expression. That's a fourth order potential. Yeah, a fourth order polynomial. And you see, there is no absolute term. So every term carries a factor r. This means it goes through 0. Yeah? Now calculate the derivative at 0. The derivative of 0 is given by this term. It's negative. So it goes through 0 with a tangent like this. And on the other hand, it's a polynomial of fourth order, so it cannot have more than 4 zeros altogether. 1 0 is here. 2 zeros we want to have here. So there must be a fourth one, and obviously it must be here. Yeah, if you just look at the picture. So the only possible geometry for the potential would be this here, for bound orbits. It must be like that. Whenever the function has a different shape, a bound orbit is not possible. Yeah? So we have to find out these values for E and L for which the potential has this shape. It means it has the 0 at r equals 0, which the potential always has, and then it has 3 positive real zeros. And we denote them in the following way. We call this the apocenter. If our center would be the sun, in Greek helios, we would call it the apohelion. Yeah? And this, the pericenter, no, this one here, sorry, here is the bound motion. So if our central object would be the sun, we would call it the perihelion. If our central object would be the earth, we would call this apogee, from Gaia, the Greek word for the earth, and this is a perigee. And if it is a black hole, I've recently learned that some people call it the apobothron or the peribothron. And then we looked up what this funny word means. It is something like a fireplace which is used for an ancient cult, something like that. So that's where this Greek word comes from. So obviously somebody felt reminded of such a fireplace when you heard about black holes. So sometimes, in some papers, very recently, you find these words apobothron and peribothron. Well, if we don't want to specify what the object at the center is, then we just call it the apocenter and the pericenter. That's always correct, right? And that's the word I will use in the following. And then we have a third zero here. So this has nothing to do with our bound motion. Yeah? And I just denoted R0. You see, in this situation, our potential then obviously must have the following structure. I write the factor of the highest order term in front of everything. And I have one factor of R common for all terms. And then I must have something, something with a factor 1 in front of the highest power. So it must be of this form. And here comes the three zeros, RO, or R0, RP, and RA. So that's the way in which we can write the right-hand side. And now we can just compare coefficients. Yeah? We multiply this thing out, and then we compare where the term in front of the R4 term is automatically the same. We have done it already in this way. But if you compare the cubic term, the quadratic term, and the linear term, you get equations which connect these zeros, the values of these radius coordinates at the zeros, with our constants of motions E and L. And in this way, you could express everything in terms of RP and RA. So we could use, so characterize orbits. So originally, we used the parameters E and L, the two constants of motion. So every orbit, every bound orbit would be characterized by a pair of values E and L. But using this parameterization, we could also use the RP and the RA. This would be already be OR. Yeah? You could do this alternatively. So this is, of course, much more geometric. Yeah? If you tell me you have a bound orbit with values E and L, then I don't have a clear geometric image how this orbit looks like. But if you tell me it has this pericenter and this epicenter, then I have a clear idea. Yeah? So if the two things are the same, then I know it is a circle. If they are very different, I know it is something very, very much stretched in the radial direction. So this is actually a very convenient parameterization. To make the equation simpler, one usually does not use RP and RA, but something which is equivalent to RP and RA. And this is the so-called similatus rectum and the eccentricity. And they are defined in the following way. I write the pericenter as P divided by 1 minus E, and the apocenter, wait a minute, this is a smaller one, then in the denominator I should have the bigger thing, 1 plus E, and here P divided by 1 minus E. Well, I think you all know what this means. If our orbit would be an ellipse, which it is not, yeah, but if it would be an ellipse, then these things would have a very clear meaning and everybody knows what they are. So for an ellipse, let me draw this here. Well, an ellipse is something like that. Okay. It has a focal point. This here is a minimum distance, so this is a pericenter. This here is the apocenter, RA, and the similatus rectum is this here. This is P. Yeah? The whole thing, if you go from here to here, this would be called the latus rectum, and this is the semilatus rectum, half of it. Yeah? And this is a very convenient parameterization, and you can directly read from this expression that knowing RP and RA is equivalent to knowing P and E. You can easily solve this for P and E. And this definition makes sense for any bound orbit. Yeah, I have explained it with a picture for an ellipse, but this may be anything with a maximum radius and a minimum radius, and this definition makes sense. Yeah? And that's the parameterization we will use in the following. So what we want to find out now, oh, I'm afraid I don't make it today, is which values for P and for E are allowed for bound orbits. And this automatically will also give us the result, what values for RA and RP are valid. So I will now write my potential in terms of these things, and then I will solve the equations which arise from comparing coefficients. I will solve these for the three unknowns E, R naught, and L. And then I have expressed everything in terms of P and E. And that's what I want to have. If you allow me to squeeze this up there, the potential now expressed in terms of P and E oops. Yeah, let me write this here. Oops. Well, what was RP? RP was P divided by 1 plus E, and RA was P divided by 1 minus E. And now I compare coefficients. So I consider the third, where the fourth order term is automatically the same for both expressions. But the cubic term, I have on the left-hand side minus RS C squared divided by 2L squared. And where do I get a cubic term here? So of course I have the factor in front of everything. C4 minus E squared divided by C squared L squared. Where do I get a cubic term? Here I have 1 R, so I must get a quadratic term for, I should point to this line. I should have to get a quadratic term from this term, so I have 2 factors of R. I need 2 factors of R, and then just these 2 terms add up, right? So I have minus R naught minus P1 plus E minus P1 minus E. Actually, because I have a minus sign everywhere, I can multiply with minus 1. Then it looks nicer. So that's the cubic term. And the quadratic term, this is, what is this? Can't read this. Just the 1/2. And a quadratic term I get here from C4 minus E squared and L squared. Where do I get a quadratic term? Then I need a factor of R from this triple product. So when I have a factor of R, then 2 of the zeros come multiplied with each other. So I have R naught P divided by 1 plus E plus R naught P divided by 1 minus E, that's brackets, plus P squared 1 minus E, 1 plus E. And the last equation is minus RS. Is this a half? Yes. Minus RS half is, yes, the usual factor, of course. C4 minus E squared, C squared L squared. And now I need just a linear term. I have already 1 R in front of everything. So this comes when I get here the absolute term, where the 3 zeros are multiplied with each other. So I get a minus sign, and then I don't need a bracket. R naught P divided by 1 plus E, P divided by 1 minus E. And as I have a minus sign on both sides, I can do it this way. Well, and from these 2 equations, I can now easily determine R naught. Let me see if I can do this. How was this? Obviously, I should multiply this with RS. Let me see, I have to look this up, how I did this. Oops. Mm-hmm. 1 minus e squared. Okay, I multiply, well, let me call this here E and this F. And then I multiply this with 1 minus e squared, and I write this on the other side. So I have c squared L squared divided by c to the 4 minus e squared. I have a 1/2, and I multiply with 1 minus e squared. Let's see what I get. Do I get here? Here I get R naught P. I have multiplied with this term, 1 minus e squared. So I get here a 1 minus e plus R naught P 1 plus e plus p squared. So this would be, again, the equation E, slightly modified. And from this equation, I get Rs c squared L squared divided by c4 minus e squared. And let me divide by Rs. 2. And 1 minus e squared. I've divided by Rs, so I get R naught divided by Rs times p squared. Okay? And here, very nicely, these two terms cancel. This would be my equation f prime. If I've done it correctly, then I should be able to determine R naught. So let me see, if I subtract these two equations, I get 0, and here I get ROP, here I get a 2, and here I get what is this? R naught. Minus PRS. And then I have this term here, plus p squared. And I think I can solve this for R naught. So I get R naught is P divided by this with a minus sign, P by RS minus 2. Or let's write this a little bit nicer. PRS, P minus 2RS. And now let me check if this is correct, because then we can quickly continue next time. PRS divided by P minus 2RS. Yes, that's a crucial equation. So with the help of this equation, which allows us to express a third zero by the two boundaries of our bound motion. Yeah? The P and the E doesn't enter, but the P and the E together determine RA and RB. RA and RP. That was the notation. So if we know these, then we can calculate the third zero. The third zero is fixed by this. And with the help of this equation, we can then determine in which area bound motion is possible. So we need this equation next time. I think that's the only thing. Is that true? And we should keep in mind where the circular orbits are. Hope everybody remembers this. I think these are the two things which we need to remember. And then we can find in a PE diagram. Yeah, in a diagram where we use P on the horizontal axis and E on the vertical axis, then we find the points where bound orbits are possible. And the interesting thing is that they are not possible arbitrarily close to the black hole, and that the boundary on the left-hand side, so towards the horizon, that's a boundary on the lower side of the range of the p-values, that these are very interesting orbits. These are the so-called homoclinic orbits, which we will then discuss in some details, and the orbits close to them, these are the famous zoom whirl orbits, which we'll also discuss. So that will be the program, now I guess, for the next 45 minutes on Friday. And then we have the tutorial on Friday from this very old worksheet. This was the second worksheet, which we still have to discuss. So see you on Friday.